Hello Mathemaniacs, I'm the Math Edumacator, and today we're going to bring you another video on set theory. Having covered the cardinality of sets and some of the operations on sets, what we're going to talk about now is some additional structure to our system. In particular, we can have categories that are entirely contained within other categories. This is my bookcase. I keep most of my, books on it. Generally, I have some method for sorting these books. For example, most of my math books and books related to teaching I keep on the bottom shelf, like this one here. Other books, like novels, I keep on my top two shelves, but with them I'll usually sort them by author or series. Like here are all my Star Trek books, and here is a book called The Giver, and it's part of a series. In fact, let's talk about the Giver series for a second. See, these 4 books I could say are part of a set. But I could also describe the books on my bookshelf as part of a set, and that would include these 4. So this set of Giver novels is contained in the set of all books on the bookshelf. It's not an element of that, it has its own elements, but every element in here is also an element in here. We say that these Giver novels are a subset of all these books. A subset is a collection that is itself part of another, usually larger, collection. More on the usually later. In a Venn diagram, we can show subsets like this, where the subset is fully enclosed inside the larger set, which we call a superset. Notationally, we denote subsets using this symbol here, which we read as A is a subset of B. We also use this symbol to denote that something is an element of a set. So in this case, X is an element of A because X is inside the A circle, and X is an element of B because it's also inside the B circle. Before I go on, I have to address another important caveat. When talking about subsets, it's really important to define your sets very clearly, because both your subset and your superset have to contain the same sorts of things. For example, suppose I have a set of all movies, and I have a set of sci-fi movies, like Interstellar and Chronicle. Anything that's a sci-fi movie is by default a movie, so sci-fi movies will be a subset of movies. The things contained in both these sets are movies. However, if my big set is movie genres, then it's totally different. Now, sci-fi movies are an element of that set alongside horror movies and comedies and any other genre. If this were a set, it would contain movies, but this set contains movie genres. And so they're not measuring the same thing, which means this isn't a subset. Now, if we were to take subsets and combine with what we know about set operations, we can deduce some really interesting relationships. First, what about complements? Well, the complement of A is going to be everything outside the small circle here, and the complement of B is going to be everything outside the large circle. Well, here we can see that if I take everything outside the small circle, that's going to, by definition, include everything that's outside the large circle. When you talk about the complements, the subsets get switched around. If A is a subset of B, then B complement is a subset of A complement. What about intersections? Well, to be an intersection, I have to be both inside A and inside B. But everything in A is already inside B. So my intersection is actually just going to be A, my subset. Anytime I have a set and one of its subsets, the intersection of those is always going to be exactly the subset. Likewise, what if we took the union of these two sets? That would include everything that is in either A or B. Well, everything that's in B is automatically going to be in A. So the union would be exactly B. So anytime you have a set and one of its subsets, the union of those is going to be exactly the whole set. Lastly, we're going to talk about 2 very important things about subsets, or rather 2 things that you may not have thought of as being subsets. Take this bag, which contains 4 dice. We're going to use this as a set for our demonstration. If I reach into this bag and pull out some dice, whatever I pull out will be an example of a subset. So, like so. There you go. Red and blue. Makes sense, right? The only thing I could pull out would be dice that were in the bag, so that must be a subset of all the dice that were in the bag. Well, here's two situations that can happen. One, I could pull out all 4 dice. So my subset is the entire set. This does fit our criteria. Everything in that set was in the bag, so it must be a subset. But it does lead to some interesting implications. I said once that 2 sets are equal if they have the same elements. In practicality, the way that we show that a lot of times is by showing that both sets are subsets of the other one. If I have set A here, and everything in set A is in set B, and then for set B, everything in here is in set A, then those 2 sets are equal. They're the same set, basically. The other interesting situation is I could reach in the bag and pull out nothing. So our set is just our old friend, the empty set. It turns out that the empty set is actually a subset of every set. Explaining how this fits our criteria of subset is a little bit more complicated. For now, we can just say that it's a subset because it doesn't contain anything that's not in our superset, because it doesn't contain anything at all. So, 2 important subsets to remember: the empty set and the set itself. And that's it for today's video. Next week we'll be leaving set theory briefly to look at some other mathematical domains, but we will be back someday. And just know that if you subscribe to this video, you'll be part of a very small, special subset of the YouTube community, and one that I very much appreciate.
If you enjoyed this week's video, please like and comment below and share the link. If you want to see more, subscribe to us at the Math Edumacator YouTube channel and follow us on Twitter at Math Edumacator.